Good day. We're going to save time. If you haven't seen the prior video, watch it. It's 10 minutes long. This is the continuation. On the screen here, you see a Wikipedia image showing the nuclear force, which must be disambiguated because there is more than one nuclear force. This is called the strong force. It has a more modernized definition according to the standard model of particle physics, but that goes to a mathematic level which actually divorces itself from reality. It actually is axiomatized on an anti-scientific statement. But this curve is antiseptic. I've given several presentations on this diagram because this is the most important graph you will ever see. You're looking at the quantum, and you're also looking at the coordination of space and time. It's more complex than that, but it's actually simpler than Einstein thought, and it's simpler than Dirac thought. To just name two emblematic names for quantum mechanics and cosmology. Einstein was a cosmologist. So, what we have here are basically three objects: a vertical line, a horizontal line, and a curved blue line. The vertical line is force. It shows a deviation from zero on the ordinate, which is the y-axis. So on the far left, it's measured in newtons, which is a measure of force. It's one of the standard international units, force. What is below zero is marked with negative numbers, negative force. The numbers above the horizontal line are positive numbers. This shows the relationship between two protons at close range. I haven't said what the positive and negative aspects are. What would be positive force? And what would be negative force? And in several of my presentations, I got the force valence inverted, and several of my listeners commented on it. It's actually quite easy to do. Amazingly, this mistake that I made, which made me sweat for a couple of days as I tried to figure out why I keep making this mistake. It wasn't the first time I had gotten the force valence inverted. Below the line is either attractive or repulsive force, and above the line is its opposite. There's a similar force curve that describes the relationship between the electron and proton at the innermost shell, that is, the innermost orbital, typically of a hydrogen atom, since that's simplest to graph. But this is the proton-proton relationship, which is opposite that of the proton-electron relationship. So right away, you have to know which one you're talking about. But then, you're still not done, because which is which? It's either this way or this way. So which is it? I'm not going to say. I'll let you guess. And if you guess correctly, you'll do better than I do half the time. I'm kind of dyslexic, but that's no excuse in science. So I'm just going to let that go for now. But it is force. It's attractive and repulsive force. So zero on the vertical line means no force. Okay. So now that should help you. But now what is the horizontal line? The horizontal line is distance. It's proximity. It's the length of a distance between. Now, when you say between the two protons, you have to be more specific than that. It's between the centers of the two protons. The centers. But a proton has a radius. Let's take a look at this a little closer to see what that blue line is. That's the key to the graph, obviously, the blue line. That is not the path of the proton, and does not indicate the position of the proton, except where the blue line may touch the line of distance. And you see there's only one of those. There's only one place on this graph where the blue force line intersects the spatial line. The blue line leaves going this way. The asymptotic curve is the visual representation of Zeno's paradox. And it is the relation of a straight line, which here is the space line, with a curved line, which is here the force line, where they're not parallel and they don't intersect. So the horizontal line going off this way is going to infinity. Well, so is the force line. It's decreasing. Now, the force is not distance, so the blue line is showing a decrease towards zero force, which it never reaches. That goes to infinity, and that's profound. So that's an infinity on the graph, is the blue asymptotic line, and the horizontal line are asymptotic to infinity. They never converge, and that's Zeno's paradox. So you can think of a proton as being on the horizontal line, but if you want to visualize it specifically, 3 femtometers away from the other proton. So this graph depicts the force curve between 3 femtometers and 0 femtometers. You can see that the protons never collide. Why? Can you state that more specifically? This is the final aspect of the graph that you need to understand. So I hope I'm doing a good job. I try my best. I've been doing this for 3 years, and I've produced over 750 lectures now, which go unwatched, except for one, which got 1,712 views and then stopped. That was when I made my huge mistake in the force valence. It was that video that got all the views. 1,700 is about 3 times as many as my second most popular video, which was on the Dirac equation. There are 2 infinities here. So there's a spatial infinity going off to the right. There's a force infinity going vertically. You can see there's another asymptotic relationship where the straight line to which the blue line is asymptotic vertically is not shown, but Bošković shows it. So Bošković is ahead of all of us. Not anymore, because I read his book. I have 2 editions of his book now, and I am not done rereading that book. He's the greatest scientist who's ever lived. I'll be showing that to you progressively. This isn't about men, though, but in this case, if you're going to have a hero, it's going to be Ruđer Josip Bošković. This most popular video that I ever produced was on this graph, where I got the force valence inverted from what Wikipedia says. After 2 days of sweating this out, because that was a major mistake that I've made before. So it's a repetitive error, which, I mean, that's terrifyingly bad to get the force valence backwards. It turns out there's a reason that's deeper than dyslexia or loss of memory. My version is actually better. They repel. But if they get close enough, they stop repelling and attract. And they lock together. Well, that's the opposite of electrodynamic force balance. So what happens at the transition? This graph shows what happens. It solves a lot of conundrums in science, including the quantum paradox and the relationship between space and time, is all on this graph. This graph isn't the TOE. My translation of it leads to the theory of everything, Kirchheim-Mongel. I don't mean on his show, though. I mean just he and I. What does this graph actually show? It shows a force inversion at close range. You can see that it's not a quantum change. So that ends quantum mechanics. That is the solution. This graph is the solution to the quantum mechanical paradox. Do you know why? It's because the blue line is continuous. If it's continuous, there's no quantum jump. So why do we think that there is a quantum jump? The original quantum was discovered by Max Planck as the quantum of action. And without going into too much detail, there are several ways to define what is a quantum or what is the quantum. Currently, the Dirac equation attempts to define the quantum as a wave function. This graph substantiates that, but it defines it algebraically, therefore mathematically, which Dirac was unable to achieve. It's probability that forces the quantum jump, which Einstein raved about to his dying day, because if there's probability involved, then you fail. That's been argued. It was first argued by Niels Bohr. and it was ostensibly settled in 2022 with the very first Nobel Prize in Physics ever awarded for philosophy, probabilism in deterministic science, which is a contradiction. You can't have both. Well, it comes down to the difference between continuity and quantization. I've proved that the quantization is due to our mathematical system, which is linear. Since this is a curve, it cannot be a linear number. It can't be represented. The only linear quantity is the horizontal line because that's distance. It's a one-component number. 3.0 on this axis, 3.0, that's a one-component number. The curve is not a one-component number anywhere. It's a two-component number. That's been proved. I'll say, even if nobody else thinks it's been proved, I proved it. That's the subject of my current document in preparation. Now, we need to know what this means. A graph, just as an equation, needs to be translated into some human language, in my case English. So that's what I'm going to do now. Now you know the horizontal line is space, the vertical aspect is force, and the blue line occupies force space. It crosses over space at only one point. And that actually is a point. So, where is it? You see, the blue line comes in this way, dips, reaches its nadir, and then suddenly changes direction and goes up. You'll notice that that's orthogonal on an asymptotic relationship. This is spherical orthogonality, because this aspect is perpendicular to this aspect. Now, the blue line cannot be said to have a linear orthogonal relation. It's not depicting linear orthogonality. But you can see that it's very close to being orthogonal because of the two asymptotes. The two asymptotes are asymptotic to an orthogonally positioned pair of lines. So this is the curve of orthogonality. That is a bit abstract, but I'm trying to stretch your mind for the real punch. This has never been noticed, you understand. Even though this graph is in Wikipedia, nobody can explain what it means. Bošković explained what it means perfectly, rationally, mathematically, algebraically, realistically. Really, he got it. This is a two-force dynamic system. So that's abstract. Remember, nobody ever saw this. You're seeing it, and I'm trying to show you what nobody has ever seen. Okay? So each step is critical, but it's synthetic. Synthetic is equivalent to geometric. That's why nobody can see it in physics. It's because they don't know geometry. Well, I do. I learned it on my own and then got my PhD from Ruđer Bošković, and there's no higher authority. So I'm the man to explain this. Let's see if I can do so. This will go to a half an hour. We need now to understand four aspects of the blue line. The first aspect and the second aspect I've already covered. There are two asymptotic infinities involved with this blue line. It's asymptotic with space. It's also asymptotic with an unseen line, although Bošković shows it. It's at the 0.8 femtometer hatch, which is, of course, about 2/3 of the way between 0.5 and 1. Right over, there's 0.5, there is 1. Now you can see at the 1 femtometer range, very close to the 1 femtometer hatch, is the nadir. That is the lowest. It's not a point. One wishes to avoid the use of the word point when referring to a curve. There are no points on a curve. I proved that, so you can accept it. It should be intuitively obvious. Stretch your brain if you can't see it, because you must see it, because it's true. The only points that might exist, according to Euclidean logic strictly, are on a straight line, because that can be quantized. The curve cannot be. Not with a one-component number. I proved that the curve, any curve, can be parameterized on a two-component number, called a rate, essentially, in calculus language. But without deviating too much from what we're looking at, that should provide you with the rationale behind what I'm going to say next, which is quite interesting to try to say this. I'll always be challenged when I do this, but I don't want to stutter like Peter Voigt. And they all do. That's just single out Peter, because he's so funny. He looks like a nerd. He looks like a geek. And he sounds just exactly like the kind of mathematician that we all hate. Because you don't want to be like him. It's like, well, the string is the string with the... It's like, no. Okay, so I don't want to be like that. I want to be the opposite. So let me begin. Let me gather myself here. Okay, here we go. So those are two aspects that I wanted you to see. The two infinities. This infinity goes off that way. This infinity goes off that way. And the blue line just chases two orthogonal lines. Asymptotically, perpendicularly. That's critical to see that it's perpendicular. But a curve, that's not how we were trained in school. Well, that's part of the problem. Euclidean geometry doesn't work here because it's two-component space. The Greeks didn't know what to do with that. I'm the one who discovered it, so I'm not blaming anyone in particular. All right, so those are the two infinities. Now, what are the two other aspects of this line that I'd like you to observe? Well, look at it. You can see that there is a curve here, and then it changes direction, and there's another curve here. So those are two curves, but that's not precisely the other two things I want you to see. But I want you to see that there are two curves. And the reason for emphasizing that is that the force valence inverts at the nadir. But that's not properly true, because the only place that the force balance or force relation might invert is at the horizontal line, where the force is zero. Do you see the point where the blue line crosses? Now, let me show it to you. I'm sure you do see it, but I'm going to go up, but I don't have a pointer. But it's directly above my fingers at about the 0.8 femtometer distance. And if you go straight up, you'll see that the blue line crosses the horizontal line, which is the space line. So this is the only position where the second proton, in its proximity to the first proton, will just remain there and not be attracted or repelled, which means that the electromagnetic relation between the protons is neutralized. That turns out to be an Eulerian sphere. I discovered that and named it. Another way to say it is a Lagrangian sphere, but it's Euler who discovered the currently called Lagrangian points. But Euler only found, I believe, 2 of them, whereas Lagrange identified all 5. Interesting. The Lagrangian points are quite significant, and I've given several presentations on that, because that's how we park the James Webb Telescope, is at a Lagrangian point in spherical space. Quite an interesting thing to do. So to return to our graph, that is a Lagrangian point, because it's a zero force point. And that is imaginary. And how could I say that it's imaginary? Because the blue line crosses there, and the blue line has no points on it. So it's just an abstraction, but it's a physical abstraction. So what we want is to get the definition of that point mathematically. This is as close as we can come to doing so. And there is a huge controversy, by no means settled, on what is the radius of a proton. Well, if we could apply the calculus to this curve, which technically we can, we could get the exact radius of the proton. But here's where it gets spooky. The proton has a spherical radius, but what is that is it solid? No, it's not solid. So to explain what this graph actually shows, you have to picture two spheres. And these are protons. And if they're this far away, they drift away from each other forever due to electrostatic repulsion. And that's one way to say it. Or electrodynamic repulsion. It's plus plus, so they repel. And if they get closer to each other, they resist. This graph shows how much they resist. And there's a maximum repulsion between them at the bottom of the graph. So that's maximum repulsion. But that's not what Wikipedia says. Wikipedia says that that shows maximum attraction. After which the vertical asymptote shows infinite repulsion. Now, what I've said more than once in more than one video is exactly the opposite of what Wikipedia says. And I want to show you that you might look at it either way. If you're looking at it electrostatically, and let me give you a clue, this is not the electrostatic relationship. This is a more inner relationship, as conceived in one view. because two protons, I mean, this is so magical and weird, that these two particles repel. And if they get this close, so they're 1.1 femtometer away, and you just start action, they go as fast as they can away from each other. But they slow down as they... He said the maximum repulsion means their maximum relative velocity is at the nadir, where they repel maximally. But you can see that if you go just a little bit more, they're like, but if one has velocity, in other words, relative velocity exists between them, enough to overcome the nadir, so that, like, you know, they're like, boing, well, that wasn't enough. Boing, that wasn't enough. But if you get past the nadir, it goes boing. That's the vertical part going up towards the horizontal line. It's it's less and less. It's like maximum repulsion, but they still go, so it's less and less and less. Doesn't quite reach the horizontal line. It'll slowly go back and accelerate, and then it slows down to infinity. But if it gets far enough, like, I'll slow it down. They're coming in like this. They're slowing down because they're repelling, but there's just enough force. Gets beyond it, they bind. They bind at the crossing point because that's equilibrium. But you can see the graph shows that they don't stop. Even though it looks like they stop, as they stop positionally, so that now they're a fixed radius away from each other at the 0.84. That's the current internationally published figure, is that the binding place where they actually lock and stop, that blue line continues up. As these stop, the force goes to infinity. and doesn't stop. That's a paradox. Because you cannot have infinite force. And that's 35 minutes. I am so sorry that this... Don't forget, though, this took 100 years of the most advanced mathematics to get to this, literally a turning point. In the next video, I promise, I'll try to make it in 10 minutes, but you can see how difficult it is to limit this to a 10-minute presentation. I'll show you what actually happens when two protons bind. I haven't fully explained it yet, neither has physics, but I can do so now, thanks to Ruger Joseph Bošković. This is the Bošković force curve extended to the proton-proton relationship, which is an inner shell system that I discovered, a major discovery, far beyond anything Gell-Mann or the Hadron Collider physicists have ever surmised. I got the TOE, the theory of everything at the quantum level, which explains the union of gravity and electrodynamics. And I think you're going to be surprised, very pleasantly surprised, because you're going to know more about reality than any of our physicists or mathematicians have ever dreamed. It makes total sense and explains the whole universe dynamically. That's the TOE, the theory of everything. Kurtjai Mungel should be aware of this because his channel is called Theories of Everything, or theory. I don't know if it's singular or plural. Currently it's plural. It's actually fractalized, and it will continue to fractalize, and Eric Weinstein really loves that because it gives scum like him an entry into the holy place. I kicked him out. I have that right since I have the right answer. Eric has the opposite. He has the wrong answer. He wants to emphasize, oh, keep going, kids. I'm doing it. I have geometric unity, says Eric. No, you don't, Eric, because you don't know geometry, and you're against the idea of unity. That's anti-science. That's Eric Weinstein. I am the good to his bad. And Larry Krauss is the ugly. So now you have the good, the bad, and the ugly. I'm Clint Eastwood. I don't think I do that very well. Right, this is Anna Galactic giving you the secrets of the universe. Stay tuned, we'll be right back.